Verification Corner!
Hello, welcome to Verification Corner. I'm Rustan Leino. Today we're going to look at concurrency. So concurrent programs have more than one thread of control, which means that one of the things you have to worry about when reasoning about the correctness of the program is, can a particular thread write a variable? Can a particular thread read the variable? And you need a system to be able to specify which threads can read and write which variables at which times. So that's what we're going to take a look at. Hello, I'm Rustan Leino.
And I'm Peter Müller.
So, Peter, you're a professor at ETH in Zurich. What do you do there?
Right, exactly. So I'm interested in programming and programming languages and all kinds of tools that make programming better and safer.
Ah, and today we're going to look at Challis, which one is one such tool. What does Challis do?
Challis is like a toy language which has a little verifier that actually helps you to prove that your programs are correct. And the interesting aspect is that Challis handles concurrent programs.
And how does it handle concurrent programs that other verifiers do not do in the same way?
Well, the key idea is that Chalice has a model of permissions, so it makes sure that no two threads can access the same variable at the same time.
And these permissions, do you have to specify them, or are they dictated by the system somehow?
Well, it's probably best if I just show you in a demo.
Okay, all right, let's take a look.
So here I have a little class which is called Apollo, and for now it has only one interesting method called set. And this method has a local variable called number, and I want to assign the parameter n to number, and then I want to prove that this assignment actually succeeded, so number is now equal to n.
Well, that seems pretty obvious here.
Right, exactly. So of course this verifies, you see no complaint here from the tool. But it becomes more interesting if we make the number here a field of the class instead of a local variable. So I just move this number up here. And now you will see that the verifier kicks in, and very soon you will see a complaint from the verifier. Here it is. So if I move the mouse over these red squiggly lines, you will see that the verifier complains that the location might not be writable.
So instead of complaining about that the assertion might not hold because other threads may also have touched the same variable, we get the complaint already when we try to write the variable that we don't have permission for it.
Exactly. So every method, every thread must make sure that it only accesses locations it actually has permission to do so. And since we want to verify methods modularly, so one method at a time, we specify the permissions as part of the method specification, like as part of the precondition or postcondition. Like in this particular example, I can give the method set here a precondition using the keyword requires, and then I can say I want an access permission to this dot number. And if I do that, then the error message will disappear, because now we have the permission to read and modify the number field.
So access is a part of the specification language in Challis, and it says then that on entry this method needs permission to number.
Exactly, that's how it works. So now we could, for instance, go down to our main method here and call the set method. So what we could do is we could declare a local variable Apollo and create a new Apollo object here. And now on that new object we could call set and, for instance, set the mission number to 5.
And how do we know that it's 5 afterwards here? Can we, you need to call it apparently.
Oh sure, the syntax in Chalice requires a call keyword here, and that's why the parser was not happy here. Well, let's see. So let's, for instance, put a similar assertion down there and say, well, now we want to make sure that Apollo.number is now actually equal to 5. That's what you would expect from a set operation, right? And as you can see, we get another verification complaint. So when I show you the error here, that location might not be readable. Do you have an idea what might be going on here?
Let's see. So it was writable at the time that we allocate the Apollo object. Then we were calling the set method, which requires access to the number. But why don't we have access to the number after the call?
Well, the idea is that permissions are really units that you can pass around between methods and later also between threads. So what we do with our precondition for set here, we pass the permission for this .number to that method, but then it stays there. We don't give it back to the caller. So the caller actually loses the permission and therefore is no longer allowed to access the field.
So the preconditions here play a larger role than what we have seen in other verification corner episodes in other languages, in that it actually transfers permissions as well as just stating something about what the program states.
Exactly. You can view specifications as having a certain operational meaning. They pass around permissions.
So can we then pass the permission back?
Sure, we would do that via a post condition. So I can just use the same expression here, access to this .number, and when I put it in the post condition, that means now the method takes that permission and gives it back to the caller. And now you see my error down here disappeared, but now I get a complaint for the assertion. And the assertion just says that, the error just says that this assertion might not hold.
Okay, so it doesn't know that it's actually 5, but we are allowed to read what the number is.
Exactly. And so the reason for this complaint is again that we verify one method at a time. So our verifier does not look into the implementation of set, it only looks at the specification. And the specification does not tell us anything about the behavior of set. So if you want to express that, we would have to add a second conjunct to our post condition, and you could, for instance, say that now number is equal to n.
Okay.
And if we have such a post condition, then verification succeeds.
Excellent. All right, but this is still a single threaded program.
Right, exactly. So what we could do, for instance, we could add more methods to our program. For instance, let me add a method that actually launches our mission. And well, for now, let's just use an empty method body. And we could have another method which allows the control center to observe what's going on here, and it's also just an empty method. So now I can go ahead and start new threads, fork new threads to actually call those methods. So Chalice provides a fork keyword for that, and what you get back from a fork is a thread identifier. So I would say my thread identifier 0 is what I get back from forking Apollo.launch. And very similarly, I fork another thread, which gives me back another thread identifier, and that one will execute Apollo.observe. All right, and well, we could just assume that these methods operate for some time, but eventually the mission will terminate, right? And then we can join our two threads using the thread identifiers. So I join both of them, and then our whole program, typo, could terminate.
Right. Okay. So the main forks off 2 additional threads and then joins them and then terminates.
Exactly.
Okay.
So now the interesting part is how permissions handle concurrency in such a case. So let's just assume that both our methods, launch and observe, want to access our field number, right? Then the question is, will those methods just read the number field or will they modify it? Let's just look at the read case for now. Like for instance, our launch method could do something like if number is equal to 13, then we will get a certain behavior which we will specify later.
Okay.
So now what do you expect to happen?
Well, let's see. So number is being read, so it seems, I'm guessing the red squiggly tells us we don't have access to number, just like we had before in the main method.
Exactly.
So I guess we should require access to number as a precondition to launch.
This is exactly what I did here.
Okay.
So so now the verification error will disappear. But we have a second method, right? And we assume that observe will also want to execute or access number in a way. So I would put this would have to put a similar precondition here.
Okay.
But now what you will see down there is that the second fork here reports an error because it says that we don't have the precondition for the observe method. The reason is that we had an access permission for number, but we gave that permission to the launch method. And that thread now is running and it holds on to that permission. So now the permission is gone and we don't have another permission that we could give to the observe method. So that's what will later ensure mutual exclusion, right? Only one of the two threads can have the access permission to the field.
That seems good, but in this case we actually want the two to access the number field. So what can we do then?
Exactly. So for this case, Chalice provides also read permissions. So if I replace this ACK predicate here by an RD predicate, that means give me some permission but not the whole permission. And as soon as you have some permission, you are allowed to read. Okay, and I can do the same down there. And now you will see that the fork succeeds.
There we
Okay,
are.
because they can both read. And now if I attempted, for instance, in method observe to update number, then that will fail because I only got a read permission, so I'm not allowed to modify the field. So there's the error message.
So the specifications here in Challis would allow us to write down which methods need to have access, either write access or read access to which variables. That
Exactly.
seems good in a concurrent context.
Right, and one particular nice feature is that, of course, we can also use the read predicate in post conditions. So let me also write a post condition for launch that gives the read permission back to the caller. And I will do the same for observe. And the nice thing is that when you fork a new thread with a method and then you join the thread again, then you get the permissions that are in that post condition. So now basically if we go down to our main method here, now what we have here before the fork, we have a full permission. And now we give away two read permissions. And when we join the two threads, we get our two read permissions back. So now we have the full permission again. So now what I could do here is I could go ahead and just update Apollo.number to 14, or use the set method for that, and that verifies.
Excellent. So what we've done here then with the Apollo object in the main method is it's allocated, and for a while main has exclusive access to it, so it can call methods on it and check that the number is whatever we set it to. And then we fork off two threads that are going to concurrently read it. And after joining those two threads, we get the read permissions back, which means we're now in a situation again where no one can read it other than the main method. So we have full permission and can write to the number field.
Yeah, that's
Excellent.
exactly what's going on.
So that's a pretty fluid lifetime of this object, that sometimes it can be written by some threads, sometimes read by them, and here we regain control over writing.
Right.
Great. Let's see, but so far the class is just reading fields, so we're giving read access. Could we let launch and observe do some writing?
Of course. So usually when you want several threads if you want to allow several threads to write a location, then you need some form of synchronization, right? And like the standard way of synchronizing such examples would be to use locks. So what we do in Chalice is, like in Java or C#, we associate every object with a monitor, and so we can use that monitor to acquire locks, and we can also associate the monitor with a monitor invariant. So let me show you how that works.
Okay.
Let's introduce another field that we will use for modifications here. So I introduce another field here, which I will call log, and its type is a sequence of strings. And I assume that while the mission runs, we will append all kinds of messages to our log here.
Excellent.
And now I can also specify an invariant, and that invariant is not an object invariant, it's a monitor invariant. So you get to assume it every time that you acquire an object, and you get to prove it every time you release the object. And the neat thing is that you can also put permissions into the monitor by just putting the permission predicates in the invariant. So now what I can say is I can put a write permission to log into the invariant. Now every time a thread acquires the log, it will get write permission to log. And of course I can also specify other properties, like for instance I could say that the length of the sequence must always be greater 0, so we do not allow an empty log here.
All right, so that invariant, the monitor invariant, is then something that holds for the object when no thread has acquired that object.
Exactly. And so Chalice really distinguishes between thread local and shared objects. So shared objects are those for which you compete using locks. And a thread local is one where one thread basically manages the permissions, maybe gives them out to another thread. So what happens is when you create a new object, it starts off as being thread local, and that's what we've seen so far.
In the main method.
Exactly. But now we want that method to share the object such that our two threads which we fork down there can compete for the lock.
Oh.
So the way we do that is via a special share statement, so we can just share our Apollo object, and now that takes a thread local object and makes it shared, makes it available for locking.
Oh.
Oh, but now we have an error message here.
And
So
what is
let's
the
see
complaint
what's
now?
going on here. It says the monitor invariant might not hold.
Aha, so when we share the object, we must make sure that the monitor invariant holds, so that it's always the case that when an object is available for to be locked, that the monitor holds at the time that the thread acquires the lock. Right?
Exactly. So let's see, we had two conjuncts in our invariant. The first one was that we want full permission to the lock field. And that seems okay, right? Because we create a new object here, so we have initially full permission to all of its fields, in particular the log field. So that's fine. But the second conjunct says that the log sequence is non-empty. And well, when we initialize a new object, then it's possibly empty, right? We don't know. So we have to make sure that it's actually non-empty. So what I will do here is I will just put an assignment that says apollo.log gets a sequence, so we can just use a sequence of one element, and I'll put something like mission started, just a string literal in there, and oops, wrong keyboard. Okay. And there we go. Now I verify. So now we have set up our object for sharing, and now the methods launch and observe can go ahead and actually share the compete for the object.
Now, in a language like Java or C#, there's no share statement. So what does one do there instead?
Good question. So the share statement here is really just a ghost operation. It's just an instruction that tells the verifier that now you switch to a different kind of reasoning, basically. And that's something that you don't need when you actually execute the program. So that's something that you only need to help the verifier along, to tell it whether you want to assume the invariant now or whether you're still in the thread local state where you can work on that as kind of ordinary data.
But it makes it explicit in the program text at the moment at which we intend to share the object.
Exactly.
Which those other languages do not. You might write as a comment.
Exactly, and that's by far not obvious, right? Because even without the share, we have already seen that several threads accessed that object, but we had to give those threads explicit permission to do so. But now with the share, we say, okay, now they can compete for the lock, and that's something that is implicit in other languages.
Excellent.
All right. So now let's go ahead and let's just use that new feature. So in our launch method, I can now, for instance, acquire the lock for our Apollo object, right? And then to show you that I have actually received write permission now to the log, I can do something like log gets whatever we had in the log before.
Oops. Let's see.
Oops, sorry, I jumped down there. So whatever I had in the log before, and then I use concatenation, and now I add another sequence where I put another string constant. So if our mission is 13, then we can use the sentence Rustan, we have a problem.
Excellent. All right.
And now you see that you don't get any complaints about write permissions, because we do get write permission from acquiring the log. So if I move that statement after the log, I've shown you that earlier with a number, then we would get a complaint.
All right.
So that's about everything that I wanted to show you about Chalice. So you see the key features are that we have permissions that kind of guide the way how you write specifications. We have read permissions and we have write permissions, and we can also have like more specialized kinds of permissions, which would be too difficult to get into right now, but you can really kind of express many different ways of thinking about a concurrent program using this permission model.
Excellent. And the permissions, like the write permissions and the others, can be passed either as pre and post conditions, or they can be acquired, they can be put into the monitor by the share statement, and then gotten from there using the lock statement.
Exactly, that's the basic mode of operation.
Great.
And now you could easily think of more features where you want to pass permissions around. For instance, we have channels, so we can have message-based concurrency, and we can send permissions over channels and features like that.
Oh.
So it's really a very expressive model that's basically like the basic layer of reasoning, and then you can put more advanced features on top.
Very flexible. Very nice. All right, let me summarize. In this episode of Verification Corner, we've seen concurrent programs, and there are a few more things to think about in concurrent programs, because with several threads of control, you need to worry about which threads can access which variables at which times. And one way to specify that is, like in Challis, to use permissions that can be written in specifications and used by the verifier. So you've watched Verification Corner. I'm Rustan Leino.
I'm Peter Müller.
Program safely.
Verification.